Hello folks, today we're going to be going over the 25s. It's what's known as a dry lab where we can run through all the mathematical calculations for the lab that we're going to do tomorrow. And tomorrow's lab we're going to be using the chemicals, we'll be using the torches, and we'll be solving or working through the lab. I'm going to read the top to you of the 25s. It says many ionic compounds are hydrated. Ionic compounds are metal with a non-metal compound. So a lefty on the periodic table with a righty on the periodic table are hydrated. This means they have water attached to the rest of the molecule. So being hydrated means there's water locked up inside that ionic compound. On the other hand, anhydrous is the name given to compounds that have no water attached. Anhydrous might be thought of as like dehydrated. There's no water there. Formulas for hydrated compounds show that water is kind of an addition to the main formula of the compound. And what I'm talking about with that is this part right here. That's how we write a hydrated compound. We add the water into it. So for example, iron 3 chloride hexahydrate has 6 water molecules attached to it in the hydrated state. And the formula is FeCl3. And then it looks like a multiplication sign. It's not. It's just a symbol that chemists use. That dot doesn't mean anything but these molecules, these 6 water molecules, are locked up inside the FeCl3. Anhydrous iron 3 chloride is just FeCl3. One method to calculate the percent water in a hydrated compound is to use molar masses on the periodic table. So we're going to go through the work to figure out the percent water with FeCl3 and 6H2O. So right here we have our name, right here we have our formula, and our goal is to figure out the percent water in this compound. So in FeCl3 6H2O, I would write Fe right here, like I have it. I have one of those Fe's. This is the molar mass off the periodic table, and this is the mass of just the iron in the compound. And then I'm going to do the 3 Cl's right here. So I write down Cl. I have 3 of them. This is the molar mass off the periodic table, and this is the mass from just the chlorines. And then I do water, and that's different. We don't break it into hydrogen and oxygen. We keep the water together. So we have 6 of those waters. Right there's our 6. The mass of each water molecule is 18.00 grams per mole. 2 hydrogens, both at 1.00, plus the oxygen, which is 16.00, gets us to 18.00. And I do the math, and I get 180.00 grams per mole. I take this 55 and I add it to the 106 and I add it to the 108, and that's where I get my 270.20 grams per mole. That is the molar mass of FeCl3 6H2O. That is the molar mass of that compound right there. When you do this lab, you'll be doing the exact same thing. You'll be breaking it down into the individual elements, how many of the element there are, taking the molar mass of it, getting the total mass of that element in the compound. Then you'll be doing the next element, and then you'll be doing it for the waters and getting a total mass. That's going to be one of your first steps. The next batch of work that we're going to do is this work right here, where we're going to start calculating the percent. So anytime we calculate the percent of something, like let's say we're calculating the percent they got correct on a homework assignment, we would put the number correct on top, correct on top, and the total number of questions on the bottom times 100, and you get the percent. So we're going to be doing the same thing, part divided by total. The part you want to know about divided by the whole thing. So here we're going to find in this step right here the percent iron in our compound. So we take the mass of all the iron, we divide it by the total mass of the entire compound. Remember, that's the FeCl3.6H2O. We multiply by 100, and with correct sig figs, there's 4 there, there's 5 there. We don't count that, that's not data, so our answer has 4 sig figs. Then we do the exact same thing with the chlorine. So we take the total mass of all the chlorines, put that on top. We take the total molar mass of the FeCl3 6H2O, We multiply by 100. Here we have 5 sig figs. Here we have 5 sig figs. We don't count the 100. And here we have a number that goes with 5 sig figs. And then we do the water. So this 108.00, that's right there. That's the total mass of the water. This is the total mass of the compound multiplied by 100. Again, 5 sig figs there, 5 sig figs there. We don't look at the 100 as a piece of data. And so we get a 5 sig fig number. And this should always add up roughly to 100, but because of sig figs, this might change a little bit, okay? The addition rule, if we follow it, this one goes to the hundreds place, thousands place, so your answer could be no more precise than your least precise piece of data. That would be the 7 right here, so our number goes to the hundreds place with the 100. So where does this come in? Well, tomorrow's lab is all about finding the percent water in the compound, so finding this number, and that will lead us to how many water molecules are in the compound. So this is what we're going to be trying to figure out tomorrow, and that's what this dry lab is all about. So this percentage will help us identify how many water molecules are actually in the compound. So that's what all this work was all about. So now we're going to do this, but for a trihydrate compound. So I want you to pause the video. I want you to start to fill in the blanks. So we did a little bit of the work for you. And again, this is right off the top. This didn't change at all because it's still Fe with 3 chlorines. So I want you to write the compound FeCl3.3H2O. That's a trihydrate. Is what percent water? And we're going to do the work for that. So this initial work right here has not changed. But now we have 3 water molecules in it. So I want you to pause the video and fill out as much of this as you possibly can. And then turn the video back on and see if you did it correctly. If you got stuck, play the video a little bit further. And then at that point in time, pause the video and go through it. So assuming that you did pause the video, 3 times 18 is 54.00 grams per mole. Okay, and we don't look at this 3 as a piece of data, so we just look at the sig figs right there, so that's why we went to 4 sig figs. We total this plus that, and then we get a grand total. And if we do that grand total, it should be 216.20 grams per mole. Okay, so you should pause the video and now calculate the percent water for all of this compound. So now we're going through and we're going to start calculating the percent water with this. So I take the 55.85, which is my grams of iron, and I'm going to divide that by the total, which is right down here, part divided by total. So I'll bring that right up there, 216.20. I have a 4-digit number divided by a 5-digit number. If I calculate that outright, I get 25.83%. Now, if you're not doing any of this work yourself, you should absolutely pause the video because you're going to get nothing out of this if all you're doing is watching it. All right, so that one is done. That percent iron. Now we got to do the percent chlorine. So I take the total mass of the chlorine, I put that right there. I divide it by the grand total, which is 216.20. Each of them are 5 sig fig numbers, so I'm going to get 5 sig figs for my percent. And that's what I get. And if you're Sandy Sorensen, you have to go down to the main office right now or call the main office. All right, on the bottom, we said this is 54.00. So we take 54.00 divided by the total, 216.20. 4 digits divided by 5 digits, so we should have a 4-digit answer. Our answer ends up being 24.98%. We could add all those up. We would get 100% in this case, and we do go to the hundreds place because that number goes to the hundredths. This number goes to the hundredths. This one goes to the thousandths. So your answer could be no more precise than your least precise number. But do realize sometimes you will get the answer like this, maybe 10% or 0.01% or maybe 99.99%. Just because of the sig fig rules, okay? So we just calculated that this compound is 24.98%. So 24.98%. That's what we just calculated. So now what I want you to do is, well, I'll read this to you. It says, in a simple experiment, 2 chemistry students took 33.68 grams of hydrated iron 3 chloride and heated it with a Bunsen burner. After cooling the beaker and subtracting the weight of the beaker, there was only 2.21 grams of substance left. Fill in the blanks and calculate the percent water. So this is how many grams that they started with. So the mass of the hydrate, how much did they start with? They started with 3.68 grams of hydrated compound. So pause the video, see if you can fill in these numbers. If you can fill in these numbers, you're going to have a really easy time in lab. If I have to do it all for you, you're going to have a more difficult time in lab. So try to do these numbers. You get some wrong, you get some wrong. So the mass of the hydrate, 3.68 grams. Right there, that's the hydrated compound. What's the mass of the anhydrous residue? Remember, that's the dehydrated stuff. That's the stuff without water. So if we look here, it says after cooling the beaker and subtracting the weight, there was only 2.21 grams of substance left. So what happened is we heated it up and the water got driven off from the compound. So what is the mass of the anhydrous stuff? 2.21 grams of anhydrous material. So how much water was lost? How many grams of water? What would you have to do that? Well, this is the compound with the water in it. This is just the compound. So if I take this number, subtract that number, I should get the mass of the water. The missing mass is from the water. So if I do that, I get 1.47 grams. What's the percent water in the hydrate? Well, part that you want to know about, divided by everything, or the total, times 100 gets you your percent. So the part we want to know about is water. So I better put the grams of water on top. What's everything? Well, this is everything. It's the compound with the water. So 3.68 times 100. And if you do that math correctly, you get 39.9%. Again, we can only have 3 sig figs because there's a 3 sig fig number on top and a 3 sig fig number on the bottom. So what's the formula from the chart above? Well, if we look at that chart above, we did one with 6 waters. That was the top one that we did, or that was done for us. And then we did the next one with 3 waters. So what we would do is we'd match this 39.9% to those two. So if we go back, our percent water, this one was 24.98% water. In the one that was done for us already, we got 39.970. And what we just calculated was 39.9%. That's pretty darn close to the actual data. So when you do a lab, there is a percent error once in a while. It doesn't always match up what theoretically should happen. Theoretically means everything happened just like it was supposed to. There was no mistakes. There was no errors. Everything was done. So if we had to match it up with those two, we would say this one has 6 water molecules to it. Okay. So again, this matches the percent water for the 6 water molecules, or the hexahydrate. So on the back side, everyone at home is going to do magnesium sulfate. So you should circle that one. Everyone at home is going to do magnesium sulfate. You're going to work through that data, and we're going to try to figure out how many water molecules are in magnesium sulfate. So we're on the back side right now if you haven't realized that yet. So you got to fill out this chart for magnesium sulfate. So what is the formula for magnesium sulfate? So we got Mg and we got SO4. And magnesium, we need to figure out its charge. And its charge is a 2 positive. And sulfate, which is a polyatomic ion, so it's found on the backside of the periodic table, is a 2 negative. So our formula is MgSO4. And if we look here, it doesn't have any water molecules attached to it. It's anhydrous, or what we would call dehydrated. Molar mass of the water molecules. So just the mass of the water molecules. So there's 0 water molecules in this compound. So 0 times 18 equals 0 grams per mole. What's the total molar mass of the compound? Well, we'd have to look it up on the periodic table. We'd have to find the mass of 1 Mg, 1 S, and 4 oxygens. Pause the video, do that. Hopefully it did do that. You got 120.36 grams per mole. And then the percent water in the compound. Well, there's 0 grams of water in the compound. And the total mass of the compound is 120.36 grams per mole times 100. So you're going to get 0% water in the compound. We're going to do one more, and I'll get you the feel for what's going on. And then you're on your own to fill out the rest of them for magnesium sulfate. So now we're going to pretend that this magnesium sulfate has 1 water molecule to it. So the formula would be MgSO4 dot 1H2O. And if it had 2 water molecules in it, it would be MgSO4 2H2O. So that's what you do all the way down the line. So for the monohydrate, how many water molecules are there? There's 1 times 18, and you're going to show your work just like this as we're going through it. And that's going to be 18.00 grams per mole. So I put that down. What's the total mass of the compound? Well, I'm going to have this 120.36, that's the dry, plus this 18 right there. So if I do the math on that, it's 138.36 grams per mole. So you notice this one, this green one, is 18.00 heavier than this 120.36. So what do you think the mass of the one with the 2 water molecules is going to be in it? Well, I'm guessing it's going to be 120.36 plus 18 plus another 18 because there's 2 water molecules there. What's the percent water? Well, if I did the math, 18.00 divided by 138.36 times 100. And if I do the math, I get 13.01%. So I'm going to have you do that work, do the rest of the work. I will give you a couple numbers, and you can check if you're going and doing things correct. So for this dihydrate, I will give you this number, 23.02%. If you don't get 23.02%, you are doing it wrong. So that's one little bit of information. I'll give you this trihydrate mass, 174.36 grams per mole. If you don't get that molar mass, you're doing stuff wrong. By filling out this chart, what we're going to do is when we do the lab tomorrow, you will put some compound into a container. You'll get the mass of that compound. You'll heat it up. Water will be driven off. We'll take the mass of the dry stuff. We'll figure out how many grams of water you have in the compound. And then what we'll do is we'll find that percent. So you'll take the water you have in the compound, the grams of water. You'll divide it by how much you started with, just like we did on this first page. So if we go back, right here, how did we calculate this percent water? We took the mass of the water and we divided it by the whole thing times 100. That's how we found the percent water. So when we find that percent water, we'll match it up to our chart here. And the one that comes the closest, that is how many water molecules you have. So it might be the one with 2 water molecules. It might be the one with 3 water molecules. It might be the one with 7 water molecules. That's how we'll find it out. So that's how we'll do the lab tomorrow. So in the wise words of Looney Tunes, yabbity, 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 that's all, folks.